Hey guys, Mr. Riss here to help you out on the third part of our 3.4 notes. And here what we're going to look at is specifically what's known as the second derivative test. And this will help us find any extrema, whether that be relative mins or relative maxes. Okay, so a couple things about this is we're going to start using the first derivative and the second derivative test together. So if you remember in the first derivative test, we can get critical numbers that are going to be either extremas. They were either relative mins, relative maxes, or in some cases we have a neither. Well, now that the second derivative tells us concavity, if we go through and plug that first derivative critical number into the second derivative and it has a concavity that is greater than 0 or positive, means it's curved up, that means that critical number would be a min. Now, if we plug it into the second derivative and it has a concavity that is less than 0 or negative, be the top of a sad point, that would be a max. So we can look at those. We don't actually have to look at the graph anymore or kind of figure this out. We can just take those numbers and plug them in. Now, if the second derivative equals 0, the test fails. That this is neither a min or a maximum, and this would actually be a point of inflection then. Okay, so we're not going to graph the points. We're not going to check to see whether the graph is going up or going down, but we're going to use the first and second derivative to determine whether that point is a min or a maximum, or if it would be a neither, a point of inflection. So let's first take the first derivative here. So what is the first derivative? The first derivative would be of this negative 3 times 5. Okay, we got negative 15x to the fourth, and then 5 times 3. Okay, then we'd get plus 15x squared. All right, so when does the first derivative equal 0? All right, I'm going to factor out a 15x squared, and this would be a negative x squared plus 1. All right, so we'd actually get a critical number here when x equals 0. And then over here, when does negative x squared plus 1 equals 0? That's when, let's see, that's just when 1 equals x squared, or when x equals plus or minus 1. So we have 3 critical numbers on the first derivative. We have a critical number, one is at 0, one is at 1, and the other one is at negative 1. Let's go back and just figure out where those points are exactly at by plugging them into the original equation. So if we plug 0 in, that's easy. 0, that'd be 0, 0, 0. All right, that's 0. All right, if we plug negative 1 in, all right, negative 1 to the negative fifth, or to the fifth power would be negative 5 times 3. Okay, that would be a positive 3. And then we'd have a minus 5, so that'd be a negative 2. Okay, so negative 1 is at negative 2. If we plug in positive 1, this would be a negative 3 plus 5. That would be a positive 2. Okay, now what are these points? Are they mins, maxes, points of inflection? Well, it all depends on what happens with the second derivative. So the second derivative, which would be, okay, negative 15 x to the fourth would be, let's see, negative 15 times 4 would be negative 60, negative 60 x cubed, and then plus 15x squared becomes 30x. What we're going to do is not figure out where its critical numbers are at, but let's plug in the negative 1. Let's also plug in 0, and let's also plug in positive 1. Okay, so if we plug in negative 1 here, we'd get negative 1 cubed is negative 1. That'd be 60, and then that'd be minus 30. Okay, that is a positive number, meaning our graph would be curved up. Now, if this is negative 1 is a critical point, while the graph is curved up, that would be a min. All right, what about if we plug in 0? If we plug in 0, that'd be 0 plus 0, which is 0. Okay, so that's not positive or negative. That is neither. This would be a point of inflection, okay, because that does equal 0 there. And then what about 1 here? If we plug in 1, what's going on here? Let's see, that'd be negative 60 plus 30. That is a negative answer. It's a critical point on a negative concavity. That would be a max. So we have our relative extremas. We know our mins and we know our maxes. Now we do have another critical number at 0, 0, but that's a point of inflection. And it's not the only point of inflection, but it is a point. So we can find our extremas, which are mins or max, by doing this. So let's take a look at tonight's homework. So you're going to go through, take the first derivative, and then use those points and plug them into the second derivative to determine whether that they are mins, maxes, or neither. So I think you guys should be okay with the first couple because they're just normal polynomials. Let's take a look at, let's do 38 and 40. Let's do some of the tougher ones together. So, okay, let's change this to x squared plus 1 to the 1/2 power. So the first derivative here is, all right, it'd be 1/2 of x squared plus 1 to the -1/2 power times by the derivative of the inside is 2x. So the first derivative is, okay, we can times that by 2, so that's just x over radical x squared plus 1. So when does that equal 0? So we would have a critical number when the top equals 0. So that would be at 0. And when does the bottom also equal 0? And if we try to set the bottom equal to 0, we'd get a -1 equals x squared. It just wouldn't work out. So we have a critical point at 0. We plug it back into the original problem. 0 squared is 0 plus 1 is 1. Square root of 1 is 1. Okay. 0, 1 is a critical point. Now, what is 0, 1? Is it min, max? Is it neither? And that determines about the second derivative. So the second derivative here, let's figure this out. Now, I might change this to, I don't like quotient rule. I'd rather do x times x squared plus 1 to the -1/2 power. I'd rather do the product rule here. So the second derivative. Take the derivative of x as 1. We'll leave the x squared plus 1 to the -1/2 power alone. All right, now we'll leave the x alone. We'll take the derivative of the second part, which we have to do the chain rule. So we get a -1/2 x squared plus 1 to the -3/2 power times the derivative of the inside, which is 2x. All right, so we would have to factor out the x squared plus 1 to the -3/2 power. And what's left over here? This would become x squared plus 1 to the first power. And then over here, we would have a x times a -1/2 times 2x, which would be a -1 x squared, so or -x squared. Wow, that's kind of nice. Because that means the second derivative is, we move this down to the bottom here. We get an x squared plus 1 to the 3/2 power, and this just becomes 1 on the top. Oh, that's crazy, it worked out that nice. So going back to this point here, 0, 1, if we plug in 0 into the second derivative, what is 1 over 0 squared plus 1 to the 3/2 power? Is it positive, negative, or 0? And in this case, we'd get 1 divided by 1. That's a positive number. So 0, 1 is the critical point of a positive concavity. Oh, that's negative. Oh my, I always get this confused because I think positive would be max, but positive is not max. Positive curves like that makes it happy. The critical point of there, that would be a min. So there is one critical point on 38 at 0, 1, or one extrema on 38 at 0, 1. That is a minimum. Okay. All right, now let's check out 40 here. All right, we got x divided by x minus 1. Okay, so we got to do the quotient rule. All right, so first derivative, we got low d high minus high d low over low low. All right, so the first derivative, we get an x minus 1 minus x, okay? So the first derivative is -1 over x minus 1 squared, right? Okay, this actually is really nice and easy because if we think about this here, we can only find critical numbers in a fraction when the top equals 0. And is -1 ever going to equal 0? No, it won't. So there are not going to be any critical numbers. There's not going to be any mins or any maxes. It's just going to be straight up, no points, no relative extrema, because the top here will never ever equal 0. Sure, the bottom would equal 0, but that's where it cannot equal 0. That'd be a vertical asymptote. So we actually don't need to do the second derivative here. There's basically going to be no extrema. on number 40, which is coming nice. Now, if the top did equal 0, we'd have to go through the second derivative test like we did before, but you notice some key things here, it actually makes it easier. And we can always double check what these look like on a graph to help us out. All right, guys, so this wraps up part 3. I will see you guys for part 4. Have a great time, and I'll see you next.